All right, so we will start the class. So last time, what we have seen is we talk about this, right? So if the limit of xn is L and yn goes to m, right? So then we talk about the limits of xn plus yn, xn minus yn, xn times yn, xn divided by yn, right? So these are the things we talk about at the end of the class, right? So I will try to prove couple of results here. The first one is right. So the first results is if xn goes to L and yn goes to m, right? So if the limit of the sequence xn is L and the limit of the sequence yn is m, then the sum of those sequences L plus x plus xn plus yn will convert to L plus m, right? So this is what we see as a theorem last time. So today what I am going to do is I am going to start proving this. So if you want to prove this, right, so obviously all the proofs here will start with let epsilon greater than naught be arbitrary. Right? So if you take let epsilon arbitrary, you know that because xn goes to L, right, there exists some n1 in natural number such that xn minus L is less than, for a purpose I am writing it as epsilon over 2, right? So epsilon over 2 for all n greater than n1. Right? So that is the definition for the convergence of xn to L. And then similarly you can write a equivalent definition for yn. So this time you will have another natural number n2, right? n2 such that yn minus m is less than epsilon over 2 for all n greater than n2. Right? So you have two set of relationships, right? So one is for limit xn goes to L and the other one is limit yn goes to m. But you know that your question is you want to have for both xn plus yn. So first you have to have a common natural number, right? So here you have n1, which is a different natural number from the other one, n2. So you have to make a common form here, right? So as Sir says in the last time, you have two light posts. So you have to make sure that you go for the common milepost. Right? So here always the common milepost is going to be maximum. Right? Because you know that here after this n1, xn is getting close to L, right? So this is L. But after some n2, yn is getting close, right? So if you go to the maximum of this, after this point, everything else will go close to L, right? So that is the basic idea, right? So you go for the maximum among those, right? And then right, so then clearly both xn less minus L and ym minus m is less than epsilon for all n greater than n. So now by using this, you can always combine xn plus y, right? right? So if you consider xn minus yn plus L plus minus L plus M, right? So that is obviously less or equal to xn minus L, right? So this and this together, and this and this together, and then you apply triangle inequality, right? So yn minus. So this is by triangle inequality. So obviously this is less than epsilon over 2, and this is less than epsilon over 2. So altogether, it's epsilon. Right? So we prove that for all n greater than n, xn plus yn minus L plus m absolute value is less than epsilon. Right? So that is what we want to show. Right? So then and so then you have xn minus xn plus yn minus L plus m is less than epsilon for all n greater than n. And so this is how you prove that limit of the sum of sequences is equal to the sum of the limit of the sequences, right? Similarly, you can do it for differences also, right? X minus yn also you can always prove, right? Same idea, right? So but only difference is here you have x minus yn, right? So for x minus yn, right? So you want to do it for x minus yn, then this has to be minus. Right? Then here you have to go for minus, and here you have to go for minus. Right? And then you can just manipulate things, and then you get yn minus m here, and it is still the same idea. Right? So that is how you prove the first results. Right? So the results involving xn plus yn goes to x plus y. Okay, so the next question is, so I will leave the minus part as a homework because it is more like a repetition of the previous word. So you can redo it again and go do for minus. So now what I'm going to do is I'm going to show you how you can do it for xn times y. So that is the another interesting part. Right, so you have to show that xn dot yn will goes to L dot m. Right? So this is what you want to show. Okay, so now what I'm going to do is I'm going to show you a rough idea first, right? How you can break this problem, right? Because addition, it is fine because you have xn plus yn minus L plus m. So you can take xn minus L and yn minus m. So that is easy. But here you have xn multiplied by yn. But you know you want to get this, right? So you have to get xn minus L is less than epsilon and yn minus m is less than epsilon. These are the two things you have, right? So from this you have to get xn times ln, xn times yn minus ln times mn less than epsilon, which is not an easy thing for you to do it at the beginning, right? So let's see how we can break this, right? So this is a rough first. And so you remember you want to get xn minus yn minus L times m. And you want to show that this one is less than epsilon, right? So that is what you wanted to show, right? So what I am going to do is I am going to break this slightly. Right? Because I want to get xn minus L, but here I have xn times yn. So if I put a yn times L, then I can factor out yn and get xn minus L. Right? So that is the first idea. I want to get xn minus L, but here I have xn times yn. So if I put a minus yn times L, I can get xn minus L by factoring out yn. That is the first thing. But this one is something you put extra. So you have to cancel that out. So you put an extra yn times L. And the good thing is you already have minus Lm here. So from this, right, if you take L out, you get yn minus m. That is also something you need. So all you do is you just add and subtract yn times L here. So then automatically you are going to have the triangle inequality, right? So this says absolute value of yn times xn minus L plus this says absolute value of L times yn minus m, right? So you have this. So now you know that you can make this less than epsilon over something, right? You can always make this less than epsilon, right? So now only problem is this one. You haven't, and this is a number. So say for example, if you make this as less than epsilon over 2 absolute value of L, then you will get epsilon over 2, right? So that's not a big deal. But here you have an issue. Okay? So you have absolute value of the sequence there, right? So which you don't know, right? So this is a fixed number, L is a fixed number, that's fine. But this is not a fixed number because n changes, whenever n changes, yn changes. So this number is going to change, right? For n larger and larger and larger, this is going to take different values. So you have to fix that value. So what is the idea of to fix that value is something which we learned in the last class or the class before that. We have a result which says every convergent sequence is bounded. So yn is a convergent sequence. So yn must be bounded. So I can make this less than some m by using the boundedness property. So you can see that in order to prove this result, you need to have boundedness condition for yn. So let us state first, right? So now by looking at this rough work, we have an idea about what we need. Right? We need xn minus L is less than epsilon over something. We need yn minus m is less than epsilon over something. And also we need yn to be bounded. So we will start with those statements. Right? So right, so I am using the abbreviations since yn is convergent, it is bounded. Right? So if it is bounded, then you can say that there x is m greater than naught, such that yn is less or equal to m for all n belongs to natural number. Okay, so that's the first result, boundedness of yn. So now we have to get epsilons or the convergence of these two results. We have to interpret, right? So I'm going to say Okay, so I'm writing the definition for the convergence of the sequence, right? Right, so I'm writing the convergence of the sequence xn minus L is less than epsilon over m plus absolute value of L, right? And there exists some n2 such that yn minus m is less than epsilon over m plus m, right? So you have two statements. So now what you have to do is you have to combine the n1 and n2 first, right? So as usual, we will take so we will take n as maximum of n1 and n2. So once you take n1 maximum, then everything else falls into place. Okay, so then what you have to do is you have to take this, right? So xn yn minus lm, right? So that you know that by what I wrote already, right? So it's less or equal to xn yn minus ynl plus ynl plus minus l. Okay, so you have that. So now once you have that, right? So you can, by using triangle inequality, you have yn times xn minus l plus absolute value of l times yn minus m. Right? So I already show you the work, right? So you have this. Okay, so once you have this, right? Now you know yn is bounded. So this is less than m, yn is less than m, xn minus l is less than epsilon over m plus absolute value of l, right? And then l plus l, yn minus m is less than epsilon over m plus absolute value of l. So if you simplify this, you get epsilon times m plus l divided by m plus l. That is clearly epsilon. So what you have is, for every epsilon positive, there exists a natural number n such that xn yn minus lm is less than epsilon for all n greater than n. So that is what you have. Okay, so that completes the proof, xn times yn part. So to prove that, you use the condition or you use the results which we already proved that every convergent sequence is bound. So we use that part here to prove. Right, so the other one, xn divided by yn, that can be also done in a similar way. So I leave that as an exercise for you. We will do it on a later time when we are doing exercises, right? So now we are going to go to a couple of more exercises, right? So I'm just going to write the exercises and leave it as a homework for you to try, right? So again, we will do it on a later time, right? So right? So these are two exercises for you to try, right? If you have a limit of a sequence, right, then absolute value of the sequence will convert to the absolute value of the limit, right? So if L is the limit of xn, then absolute value of L is the limit of absolute value of xn. And the other one is, if all the components in the sequence or all the members of the sequence is strictly positive, that means greater than 0, then the limit will be non-zero. That means it is greater or equal to 0, right? So you can notice the difference. Here every component is strictly positive. In that case, the limit is greater or equal to 0, right? So that is the another result, right? So right, so the converse of the second result is not true. If not the second one, the first one. Sorry, I wrote it wrong. Right, so the converse of the first results is not true, right? So if absolute value of xn converges to absolute value of L, right, but the sequence not necessarily converge, right? So again, you can give a counter example, right? The example -1 to the power n, right? Because you know that limit of n goes to infinity -1 to the power n does not exist, which you already know, right? You already know that the limit of this does not exist, but limit of n goes to infinity, absolute value of -1 to the power n is always 1, because -1 to the power n, whether it is +1 or -1, absolute value is 1. So that is a constant sequence. So the limit is 1. And so that is the counter example. So in most of the limit problems, you can see that if we want to disprove something, right, we always give a counter example. Last time also I gave you an example of how to write a counter example. Similarly, here also you can always provide a counter example to disprove this result. So these the first two are exercises, and also you try the exercise of xn over yn, see limit of xn over yn problem, right? So now what we are going to do is we are going to go to the next main results, which is known as sandwich theorem. Right? So sandwich theorem is, you know, the sandwich, right? So in sandwich you have a bread on the top and you have a bread on the bottom, and then you have some meat or leaves or vegetables or whatever in the middle, right? Or potato or whatever. Right? So that is the meaning of sandwich. So here we are going to do a theorem which works exactly how sandwich looks like, right? So what you are going to do is you're going to have three things. One, a sequence on the top, and then another sequence on the bottom, and then you put a sequence in the middle. Right? So you're going to have three sequences, one on the bottom, one on the top, and one in the middle, right? And in addition to that, we are going to say that the sequence on the top and the sequence on the bottom converges. Then, without any question, the sequence on the middle will also converge, right? So If both of them converge to the same limit, then the sequence in the middle will also converge. And so that is called sandwich theorem. And so this is, say, this is how you have. And so if you want to interpret this picture, right? So suppose you have a sequence which goes like this to 0, right? And then you have another sequence which goes like this to 0, right? So it's going towards 0, right? So whenever you have another sequence, right? If you say there is one more sequence, right, that somehow stays in between these two sequences, right? So you say this is your sequence xn, and this is yn, and this is zn. So you have three sequences, one on the top, one on the bottom, right? And then one in between them, right? But if we know that the sequence on the bottom and the sequence on the top converge to the same limit, then this sequence, the sequence in the middle, will also converge to the same limit. Right? So that is called sandwich theorem. And so we are going to write down the sandwich theorem and we are going to prove it. So this is always a useful result, because if you want to know the convergence of a given sequence, right? And if it is hard for you to prove the convergence of the sequence, or if it is hard for you to justify the convergence of the sequence, and if you are able to find two sequences on the top and bottom of that, and if you know that they are converging, then obviously you can say the sequence in the middle also converges. Right? So that is the idea where we use the sandwich theorem. So I'll write this as a theorem. Right? So we call sandwich theorem. Right? And so first, we assume that there are three sequences and one of them is trapped in the middle between those two sequences. Right? And okay, and then we assume that the limit of the two sequences is the same value L, right? So xn also converges to L, yn also converges to L, right? So then obviously the sequence Zn will converge to L as n goes to infinity, right? So this is the sandwich theorem, right? So we have to prove this, right? So the proof is this. So first you will write down what you have, right? So obviously you start with let epsilon greater than 0, right? And then you know there exists n1 belongs to natural number, so that xn minus L is less than epsilon over 2 or epsilon. Right, so for all n greater than n. And then for other condition, there exists n2 belongs to natural number such that yn minus L is less than epsilon for all n greater than n. Right? So these are the two results you have. Right? So these are the two results you have. Right? So you want to have, right? So Zn converges to L. So obviously you know you have to start with combining the ends, right? So because you have two ends, you should have combined it. And so clearly n will be the maximum of n1 comma n2, right? So this is what you have, right? So you choose n to be the maximum of, right? So now let us do the rough work, right? So let us do the rough work and see how we can prove it. So you want, right? You want this, right? Zn minus L less than epsilon, right? So that is what you want. So in other words, you want, right, minus epsilon is less than Zn minus L less than epsilon, right? That's an equivalent condition. So in other words, you will get L minus epsilon is less than Zn less than L plus epsilon. This is what you want, right? So this is what you want. But what you have is this, right? So similarly, from this, right? So you have so this is the first results we have xn and yn on the top and bottom and top of the zn, right? And then from this you have L minus epsilon less than xn less than L plus epsilon. And similarly, L minus epsilon is less than yn is less than L plus epsilon, right? So less than yn and less than epsilon, right? So these are the three results. This is given hypothesis, and this is again given limit of xn is L, and this is again given limit of yn is L, right? So by using these three, you want to get this result, right? So you have L minus epsilon less than xn, but you should have L minus epsilon less than n. And so I will take this part. I dropped the other inequality. I will take this part, right? So when I take this part, I know L minus epsilon is less than xn, but xn is less or equal to zn. So I have this zn. Right? So now what I do is I want this part, L minus L plus epsilon part I want, right? So I have yn is greater than or less than L plus epsilon. But Zn is less or equal to yn. And so if I combine two boxes, box 1 and box 2, you can see that I get L minus epsilon is less than Zn is less than L plus epsilon. Right? So that is what I wanted to prove. So I can easily achieve that. Right? So now we will write it down in a proper way. Right? So this is a rough work. Right? So this is the rough work we do, and we figure out what we want to do, and now we are going to write the proof in a proper way. Okay, so then you know okay, so we have right? So we have these three, right? So we have L minus epsilon less than xn less than L plus epsilon, and L minus epsilon less than yn less than epsilon for all n greater than n, and you already make n as the common n, the maximum among n1 and n2. So that's done. And also this is given xn is less or equal to zn is less or equal to y. So by combining this, this and this, you get right. So then for all n greater than n, we get right. We get is so we get L minus epsilon is less than Zn is less than L plus epsilon. So this that is for every epsilon positive, then x is n belongs to natural number such that Zn minus L is less than epsilon for all n greater than n. Right? So because you already know Zn minus L is less than epsilon is equivalent to L minus epsilon is less than Zn is less than L plus epsilon. So you can combine all of them and say that for every epsilon positive, there exists natural number such that Zn minus L is less than epsilon for all n. Right? So this is how we do the proof of Sandwich theorem. Right. So now we have to see where we can apply the Sandwich theorem. Right? So that is the next question. So we have to look for examples of Sandwich theorem. So as I told you earlier, when it is difficult for you to show the convergence of a sequence, you can always apply the Sandwich theorem. One good example is this. The sequence it is given by right so xn 1 upon n factorial. Right? For this, it might be difficult for you to figure out the natural number such that 1 upon n factorial minus something is less than epsilon, and all those things is difficult for you. Right? So what we have to do is we can apply the Sandwich theorem. Right? Clearly, you know that right 1 upon n factorial is always greater than 0, right? Because you know 1 upon n factorial is always greater than 0 because n is all greater than 0. So n factorial is greater than 0. You learn factorial in A level, right? So n factorial is n times n minus 1 times n minus 2 and so on. Right? So then it is strictly greater than 0. At the same time, you know that n factorial is larger than n. So 1 upon n factorial is smaller than or equal to n. Right? So this is true for all n belongs to natural. Okay? So you know that 1 upon n factorial is sandwiched in between 0 and 1 upon n. Right? So you know that limit of 1 upon n is 0. Right? So clearly limit of this is 0, limit of this is 0. So by Sandwich theorem, limit of this must be 0. Right? So instead of looking for the limit of 1 upon n factorial, you can easily figure out the limit of 1 upon n factorial by using the Sandwich theorem. Right? So this is the use of the Sandwich theorem. Right. So now I will give you one more exercise example as a homework. Right. Similarly, 1 upon 2 to the power n, right? So that again you can show the limit of the sequence is 0 by using the Sandwich theorem.
Not clear, sir.
Okay, so that is how we use the Sandwich theorem. So now the next one, I'm going to write down a proposition. Okay, so this is again an useful results involving the limits of the sequences, right? So if the sequence has a limit and that limit is non-zero, okay. So if the limit of the sequence xn is non-zero and if it exists and it is non-zero, then you can prove that there exists some n, right? So a certain n, and after that n, the components of the sequence xn are non-zero, right? So you can prove this, right? So here, so you take let limit of n goes to infinity, xn is equal to L. And so you take limit as L. And obviously L is non-zero. You know that. Right? So L is non-zero. So if L is non-zero, and you know you have to choose some epsilon, right? So you choose epsilon as absolute value of L. So clearly epsilon is positive, right? So this is positive. So now you know there exists n belongs to natural number such that xn minus L is less than epsilon, that is absolute value of L. Right? So that's the definition of limit, right? Right. So again, you apply the limit definition. So there exists n such that xn minus L is less than epsilon. Here you choose epsilon as it. But you have a triangle inequality which says right, but by triangle inequality, you know that xn minus L is absolute value is less than greater than absolute value of xn minus absolute value of L. The quantity is absolute value. So now you can combine these two results. Right, so you combine these two results. So this, and so obviously this one is less than absolute value of L. So I can say that minus absolute value of L is less than absolute value of Xn minus absolute value of L is less than absolute value of L. Right, so minus absolute value of L is less than or equal to this, less than absolute value of L. So if you rearrange this, you get 0 greater than Xn less than 210 absolute value of X. So this is, so you add absolute value of L on both sides. So 0, Xn, 2L. So this says right, so and you know this result is for all n greater than n. So for all n greater than n. And so what you have is absolute value of Xn is greater than 0 for all n greater than n. So if absolute value is greater than 0, then you know that component has to be non-zero, right? Okay. So because absolute value is greater than 0, so the component inside that absolute value cannot be 0. So Xn cannot be 0 for all n greater than n, and that n is this n. Right? So this is again a useful result that if the sequence has a non-zero limit, then after certain point, the components of the sequence are all non-zero, right? So after a certain n, right? So this is another results which we can use in the sequences. So what we are going to do in the next classes, we are going to see some more properties like this, right? The convergence of the sequences and some other properties, and then we are going to develop more results which will help us to understand the convergence of a sequence, right? So what other kind of sequences converge to the limit, right? So we will talk about that in Monday class, right? So yeah, tutorial, the first chapter tutorial they post in the LMS, so you can download it there. The tutorial classes we will think about that later at some time. Right? So, but the tutorial and everything we will post on the LMS. So we'll stop here and then we'll start again on Monday.